Okay, so let's start with some examples that we'll need during the course and a general description of the course. We already had a course on number theory, on elementary number theory and number systems the previous semester, and this semester we're going to have a course on common algebra and abstract algebra and some of the applications that it has in computer science even. So in computer science, many very nice and efficient algorithms are based on algebraic ideas, just as in cryptography, many algorithms are based on number theory ideas, which I don't think we had really covered that completely. The aim of this course is to summarize different structures that we have in algebra, to, name them, recapitulate maybe something, and to look at applications of these concepts, and also to look how we can perform algebraic computations in Python, say. There are many different software packages for enabling us doing the algebraic computations, but Python has its own package called SymPy, which is quite good for that, and it's free, so that was a natural choice for me. So before we dive into this whole thing, let me first ask you, because it is very important for us to be on the common ground. Let me first ask you about some of the terms that you might know or might not. This is important for me to know which of these we actually all know. So the first thing is the common notation for number sets, right? So these all are quite familiar to you, I guess. Right, so natural numbers, integers, Zahlen in German, so that's why we have Z here. In German, that's just numbers, okay? That's Q, quotients, real numbers, natural, what are these? So rational numbers, right? Reals and complex numbers. Perfect. So have you already studied complex numbers? No? Yes? Okay, just a little bit. So we just need a definition of complex numbers. We don't need a whole lots of things there. So these are number sets. Now, a concept of permutation. So what is a permutation? A permutation. What do you think of that? Like, who can remember what this is, a permutation? Okay, so it needs revision to some extent. Okay, so a polynomial. Well, it's just some kind of special kind of expression, very, very limited, just limited to multiplication and addition and taking powers of some variable, okay? So a permutation is a map, is a bijective mapping of a set onto itself. So this definition of permutation involves some other definitions that we also need to remember, like definition of a map, definition of a correspondence, definition of a relation, okay? So we also will need probably all these as well. Okay, so what about correspondence and relation? Do we need to recall that as well? All right, so let's just go and cover all this right now. Because we will not need these things like each and every time, but they just naturally raise as examples, as natural examples for some of the abstract concepts, and then to understand abstract things, we'll need to cover probably lots of examples. So relation is basically just a relation. It's basically just a subset of Cartesian product of several sets. So a relation, well, I would probably, yeah, so okay. So a relation on a set A is a subset of Cartesian product A times A times A. That sounds a bit strange. Okay, so it's not clear what this is all about. But basically, a relation is just some collection of tuples of objects in A, and we have lots of standard relations. Like we have many binary relations, right? So a binary relation is a relation where here we have just Cartesian product of A times A. So that's just A squared. And binary relations, examples of them like are multiple. Like we have a relation of equality on any of these number sets. So take natural numbers and form a relation which goes like this: n comma n for all natural numbers little n. So this is a set of pairs, and in each of these pairs we have just one element duplicated, right? So formally this is a relation which goes like this, and we do not normally write it down like this, so we treat it as a simple kind of connection symbol, equality, right? So equal numbers form pairs that fall into this relation. We never think about it like this, probably. So we also have relations like ordering relations, right? So this relation is something like n comma n, n comma n plus 1, etc. And we take all these infinite series for all the natural numbers n, and this makes us a relation like this. So this goes on the left side, and this goes on the right side of the relation. And we have lots of relations in geometry, say. So when we take lines and parallel lines, we have symbol to denote that two lines are parallel. So this symbol. And this is a binary relation which is applied, well, not applied, but it really happens between pair of lines. So two lines can be parallel sometimes. And in this case, like we talk about relation on a set of all lines that we have in some Euclidean space. So basically this provides us the ground set, so the set of objects which we are relating to each other, okay? And most, like by far, most common thing here is a binary relation. So a correspondence is a bit more general thing in a way that in correspondence we have two sets, but they may be just arbitrary. So we do not have to have the same set, but rather we can take two sets and provide a correspondence between sets A and B, which is still the same thing. So it is a subset of Cartesian product A times B. So here a correspondence may be like, well, say A is the set of people and B is the set of things or houses. And correspondence may be like the property correspondence. So if a house in B is a property of a person in A, then like we have relation, we have correspondence between this person and this house. So generally, it's convenient to visualize correspondences like this. So we just, well, abstractly denote objects in A as dots and objects in B as dots on the right. And we can connect the dots that are corresponding to corresponding objects. So if a pair of elements, one from A and the other from B, is in correspondence with each other, we just connect these two things with a line. And so this kind of picture, this, well, bipartite graph, really, this is a bipartite graph. So this provides us a visual model of any correspondence between finite sets. Well, it is not really easy to wrap your head around this thing if it is infinite, but for finite A and B, this is quite a nice visual tool. So in correspondences, anything is possible. So if these guys are people and these guys are houses, then, well, one house can belong to two different people. So they can share, they can have like shares in this house, like property shares. On the other hand, the same person, if it is a tycoon, can own several houses, right? So we can have like a single object in B corresponding to multiple objects in A and vice versa. No limitations whatsoever. And a mapping, or a map, is now a special kind of correspondence. So a map is a thing where every object in A has just one arrow to the right. Well, I can call those guys arrows pointing from left to right. So a map from A to B, a map from A to B is a correspondence where for every object in A there is exactly one object in B which corresponds to A. Which corresponds to A. And, well, we usually have a college definition of a map, which is some kind of law or some kind of, well, procedure which allows us to compute, given every fixed object in A, to compute some deterministic object in B given this A. Okay, so we have like any function is a map. So actually a map is the same kind, is the same word as basically function. They are synonymous. So this also is called a functional correspondence. A map is also called functional correspondence. Okay. So now, final thing here to define is a permutation, and the permutation is a bijective mapping of a set onto itself. So let's recall bijective, surjective, and injective mappings. Okay. Well, and basically we can apply these three terms, like subjective and injective, to correspondences, to a more general kind of object. So surjective correspondence, injective correspondence, and bijective. Well, we usually talk about bijective mappings, but it's the same thing when you talk about bijective map or bijective correspondence. So surjective correspondence, well, maybe you can recall on your own the definition of surjective correspondence. What do you think?
For any B in B, there exists A.
Mm-hmm. Yeah. So for every B in B, there exists an A. Right. So there exists an A. Oops. Such that A corresponds to B. And for us, it is convenient probably to give a name to correspondence that we are currently dealing with. So this word starts with C, and well, let's call it mnemonically, so just curly C. It doesn't really matter how we call that. So for every B in B, there exists an A such that the pair A and B falls within this set C. So on the picture, this means that there are no objects in B left behind, right? So we have no isolates in B. Every guy from B corresponds to somebody in A. And then we say that our correspondence is surjective. And as for injective, well, you recall that it's kind of the opposite thing, right? So we require basically the same thing, but looking not from B, but rather from the side of A, or no?
Yes. For any A in A, there exists B, right?
Yeah, so for every A. So it's not really just inverting this thing, because this guy, like the surjectivity, is about existence, right? And the injectivity is about uniqueness. So for every A in A, there, I would put it in this way. So for every A in A, we shouldn't be able to find two different objects in B corresponding to the same object in A. Oops, no, the other way around, right? So for every A in A, I would put A prime and A2 primes in A. There shouldn't be, right, two such A's in A, so that they correspond to the same object in B. So I can either put a quantifier here, existential quantifier, and cross it, or I could say something like this. Well, okay, I will do it with crossing the existential quantifier out. So there doesn't exist A prime and A2 primes in A that are not equal, and so that there exists some B in B, so that both A prime and B and A2 prime in B fall within our correspondence. So there shouldn't be two different objects in A, so that they have the same object in B corresponding to both of them. So in this picture, we clearly have a violation of this property, because like two guys in A, they have share in the same object in B. So that's a bit of a problem when they decide to, you know, to actually try to divide this object. So then bijective map is the simplest in terms of like how it looks like. Bijective mapping is a mapping where to every object in A there corresponds exactly one object in B, and vice versa. Okay, so for every A in A, there exists a unique B in B, so that A and B are in correspondence, and vice versa. I don't go for, you know, to shorten this definition, so let it just stay like this, because it makes it very clear like what's going on here in one-to-one correspondence. or bijective correspondence. Well, let me also write it down that it's also called one-to-one correspondence. So the picture looks like this, right? We just have every point in A sending its arrow to the right, and every point in B also has somebody in A who sends arrow to this point. So this really, in terms of graph theory, this is basically a matching. So a matching, well, if you recall it, these guys, like these pictures, they are called bipartite graphs. And in general, well, kind of picture where we have dots and lines connecting pairs of dots, they are graphs. And the bipartite graph is a graph where all the nodes, all the points can be partitioned into two sides, so that we only have links between objects belonging to different sides. And that's precisely what we have in this kind of a diagram. A special, very special kind of bipartite graph is a matching where every node has precisely one line or one edge or one link going out of this node, whatever node we look at. So node on the left or node on the right. So we have a picture like this. So these are matchings in graph theory, one-to-one correspondences. Okay, so a permutation is basically a one-to-one correspondence between a set and itself. So this is just a situation or a mapping, well, mathematically speaking, where for every object belonging to a set, we tell who, like, what other object in this set corresponds to this one. It is called a permutation because such correspondence defines really, well, a permutation of objects. How it works. So if we take an arbitrary finite set, let me write down the definition. So a permutation is a one-to-one correspondence or a bijective mapping of a set, of a finite set onto itself. So how does a permutation look like in this kind of diagram language, in this visual language? So if we just take a set and use the same set on both sides of our picture. Okay, so this is A and this is kind of copy of A. Just for the sake of drawing the picture, then the number of objects on the left and the number of objects on the right is of course finite and equal because we have the same set. And well, in general, whenever we have a bijective mapping between two sets, of course it is only possible if their cardinalities are just exactly equal. Otherwise, we cannot build a one-to-one correspondence. So if we just name these elements in set A from, say, A1 through AN, and we do the same on the right, and we take this like one-to-one correspondence, so a kind of a bipartite graph, which is actually a matching, then going from left to right essentially permutes our objects. So if you imagine that they were queued in a line, okay, so A1 was the first, A2 was the second, blah, 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 AN was the last one, then this picture really makes these objects stay in a different order. So now, like, this guy goes first, okay, or, well, I can just leave the numbers, okay? So now this guy is the first in the queue, this guy is the second in the queue, blah, blah, blah. Okay, so this guy stays last one in the queue, according to this picture. So we actually are reordering our objects when we consider permutation on a finite set. And in combinatorics, we usually, like one of the first problems that we consider is counting the number of all permutations that we have on a finite set. And by the way, how many permutations are there? So if we fix a set of, say, 5 elements, how many ways are there in total to permute the elements in these sets? Yeah, 5 factorial. Just could you remind me if you had a course on combinatorics or something? So as for like the number of combinations with replacement, multi combinations, and permutations, multi-permutations. So can I rely on that? We do have that. Okay. All right. So we actually know how many permutations there are. And also, when you study in combinatorics, when you study, for instance, inclusion-exclusion principle, or inclusion-exclusion counting formula, however we call that, one of the standard application examples is like counting the number of surjective mappings. So now we can go on with our things, but here it is. So next, I would like probably to talk about composition of mappings, and then we'll go on to polynomials. So composition of basically we can talk about composition of correspondences even. So composition of correspondences. So what's this thing? So suppose that we have 2 correspondences. One of them is between sets A and B, and the other of them is between sets B and C. So let one of them be called, say, C prime, and this is a correspondence between sets A and B. And the other of them is C2 primes, which is a correspondence between sets B and C. And what is their composition? So their composition is denoted by C prime. Then we have this little circle. Or sometimes we do not even put the circle here, but well, for starting, I will not omit it. And this guy, the composition between the composition of C prime and C2 primes, is actually a correspondence between sets A and C, which works like this. So we basically take the picture for this correspondence. So suppose that C prime looks like this. We have A on the left and B on the right. And we have some lines here. And C2 primes is a correspondence between B and C, whatever it is. And this guy, I will not draw like 2 copies of B, so I will not draw like BC here. I will use this copy of B. So let's assume that this thing works like this, okay? Let me change it a bit. Okay, so let it be like this. So now a correspondence between A and C, how can we define it? If we can walk from an object in A to an object of C in 2 steps by using first this like collection of bridges between A and B, and then following one of the bridge that we have in this collection in C2 primes, then we say that an object of A and object of C are in correspondence to each other. So this is kind of a standard concept of reachability. Reachability, like if one object can be reached from the other one. Well, just when we are talking about visualization of a single correspondence, a concept of reachability is really trivial. Like we have direct, either we have a direct connection between 2 objects or we don't. And here, when we put together like 2 correspondences one after another, like we use this concept of reachability to define a composition of 2 correspondences. So for now, for this particular picture, we'll have, like in this correspondence, we'll have what pair of objects would we have? Like this pair of objects will not be in correspondence because we cannot reach this guy from this one. As for this guy and this one, they will be in correspondence because we can reach one of them in 2 steps from the other one. And this pair will also be in correspondence, and this pair will be in correspondence. Okay? So we can define properly how this guy behaves. Now there's nothing special really about this definition, because when you apply this to maps, then composition of correspondences applied to maps is the standard composition of maps or functions that we got used to, like just from college years. So when we take like 2 functions and for like to make it grounded, let's visualize them as just functions. Okay, so let's take 2 functions, f of x, which is just squaring. Okay, and the other function is, say, g of x, which is x plus 3. Okay, so we have 2 functions. Like, what is their composition? If we treat one function as a correspondence, okay, so if we draw a picture like that for f of x, then how would this picture look like? If we limit ourselves to just integers, positive integers, natural numbers. So then we have like 1, 2, 3, 4, etc. Okay, and on the right we have still integers like 1, 2, 3, 3, 4, 5, etc. And we have the following links. So from 2 to 4, from 3 to 9, etc. Okay, so many integers on the right are actually not used by these correspondence. So they are isolates on this picture. So this is f. That's f. And now here we have g, which is also a mapping from integers to integers. So we can visualize g within this layer. Like I would again draw the 3rd copy of the natural series. And that x plus 3 is visualized like from 1 we have an arrow to 4, from 2 we have an arrow to 5, from 3 to 6, etc. So this is, well, actually this is almost a matching, but well, it is not exactly a matching because we have like 3 numbers which are isolates on the right. So this is not one-to-one correspondence between all natural numbers and natural numbers. And this is, of course, also not a one-to-one correspondence between the left side and the right side. Okay, but now what is the composition then? So the composition will look like this. From 1, we have only one way to go. So what is good about mappings is that they are very deterministic. So when we are looking at this picture and we are here, we have like 3 options where to go to the right. But if we have a genuine mapping, whatever we have wherever we stay currently, we have just one option to go. So if we stay here, then we can only go here. And if we reached here, we can only go here. Okay? So eventually from 1, we went to 4. Now from 2, we can go here and nowhere else. And from 4, we go to 7, right? So from 2, we go to 7. From 3, we go to 9, and from 9, we'll go to where? 12, I guess, right? So to 12. And then basically what we get is a correspondence, which is also a function, a map, which maps 1 to 4, 2 to 7, 3 to 12, etc. I just skipped all the numbers that are not used on the right. And this is really what we'd call in what would denote in mathematics as just x squared plus 3. Okay, so we we superimpose one function over the other one, right? So we substitute. We have a function like x plus 3, and instead of x, we substitute this guy, the x squared. Or what we also write down, we can write it down as g of f of x. So this is what it essentially is in college notation. And like in general notation, we can compose not just mappings, but we can compose arbitrary correspondences like this. So, but for mappings, it is like especially vivid and clear what's going on. Okay. So now the next thing is polynomials, which we'll also need. So polynomials, let me start wiping some things here, and I will go right to left. So polynomials are expressions. Well, we can say that expression is really just some picture, okay? Expressions that involve taking powers and multiplying by a constant, by a coefficient, right? Taking powers, multiplying by some coefficients, and, well, adding up. So for starting, this would be enough to define a polynomial. So, but already, just when we recall that polynomials, they involve just these guys, adding up, taking powers, and multiplying by a coefficient, we can concentrate on this second half, this second point of the definition, and talk about like that polynomials actually are not all born equal. And we can have polynomials where coefficients are restricted within some sets. Like in mathematics, we can prove that some theorem that it holds for all integers. And then we can prove a different theorem that holds for all rational numbers. Okay, and then we can have another theorem that holds for all complex numbers. And these would be like 3 different theorems. Now for polynomials, for this object, we also can restrict like what set can we take our coefficients from. So we actually get a definition of a polynomial over some set. So for now, I will not talk about polynomials over a ring, because we haven't yet studied what a ring is. But let's already provides the notation, and call it for now polynomials over some set. Well, you see all these guys like N, Z, Q, R, C, they all are written in like blackboard bold font. And I will use this letter F to like kind of as a substitute for almost any of these guys for now. So instead of F, imagine that there can be like anything like this, like Q, R, C, and Z. And well, eventually we'll even have something different, something completely different other than these sets. So polynomials over F are polynomials where coefficients that we use, they are only taken from this set F, okay? Coefficients taken only from F, whatever F is. Also, let's recall that polynomials do not necessarily need to have only one variable. So polynomials can have multiple variables. And the general notation of polynomials that have coefficients from F and that have variables like x, y, for instance, is like this. We put the name for the set of coefficients that we use, then we put square brackets, and then inside these square brackets, we put the variables that we can use in our polynomials. And we can easily have more than one variables. Like if we put just one variable, this is our standard kind of notation, right? So these are like, well, let me just have the most concrete notation possible. So we can take rational numbers as coefficients, and we can have only one variable x. So examples for that are like 1 over 5, just a free term. Okay, we can have a constant as a special case of a polynomial. So this is a polynomial. Like x plus 1 is also a polynomial. We do not have explicit coefficient here, but we can treat this x as like 1 times x. So we can say that, okay, so every term here in this addition has some coefficient. Now say x squared plus x cubed minus 1 over 2x is also a polynomial. Again, coefficient 1, 1, minus 1 over 2, etc. Right? So now when we just use different variables, like say x, y, z, it means that we can take powers of these variables, combine them, and build up much higher diversity of these terms that we add up. So we can take any power of x, like x cubed, for instance. We can take any power of y, like y to the power of 5. And we can take any power of z and like take this product. And this will be a single, what we call monomial in our polynomial. So every term that we add up is called a monomial. Okay, so this guy is a monomial, this is a monomial, this one is a monomial as well, and we then add them up. So we can form this kind of monomial. We can take just a single variable and use it in our monomial. And we can multiply these guys with different coefficients. But if I put z here, it means that I cannot, use say 1 over 3 here or square root of 5. I can only use integer numbers. So I can say like minus 2 plus 7. And now this will be a genuine polynomial which belongs to this set. Okay, so these are the variables that can be in the polynomial. They do not necessarily all have to be in this polynomial. So if I write down this expression, this will still be a polynomial belonging to this set of polynomials, to this kind of world of polynomials. I haven't used z, but I could. Okay, these guys are monomials, right? So this is a monomial, this is a monomial. The degree of the polynomial is the highest degree of monomials, as you recall, right? So the degree of this polynomial is 0 because we do not have x even to the power of 1 here. The degree of this polynomial is 1. The degree of this polynomial is 3. The degree of this polynomial, now for polynomials of many variables, we have two different definitions of degree. We have definition of a kind of complete degree or total degree of the polynomial, which does not involve any specific variable. So the degree of this monomial is 2. The degree of this monomial is 3 plus 5 plus z. So the total number of terms in product that we get here. So we have like 3 plus 5 plus 1 is 9. So the degree of this monomial is 9. And then the degree of the whole polynomial is the maximum degree of the monomials. So the degree of this whole thing is 9. But for polynomials that have multiple variables, more than one variable, it is also important to consider the degree of the polynomial over some variable. And then we kind of take only this variable and count only the powers of this variable inside our polynomial. So the degree of this monomial over x is 2. The degree of this monomial over z is what? 0. 0, exactly. And then the same goes for each monomial. So the degree of this monomial over x is 3, over y it is 5, and over z it is 1. And now the degree of a polynomial over some variable is still the maximum of the degrees of this polynomial over that same variable. So the degree of this polynomial over x is 3. Well, let me provide a different example. Like in this case, the degree of this let me put it differently. Okay, so the degree of this polynomial over x is 4 because the maximum degree of x that we get in monomials is 4. But this monomial is monomial of the highest degree respective of x, but it's not the monomial of total highest degree. The total highest degree is this one, so it has degree 9, 3 plus 5 plus 1. But when we're just considering the degree over x, then this guy wins, right? So the degree of the whole polynomial over x is 4. The degree of the polynomial over y is 5, and the degree of the polynomial over z is 1, and the total degree of the polynomial is 9, provided by this guy. So just two different ways to compute a degree, a total degree or a degree over some variable. That's it. So when we take sums and products of polynomials, I guess you recall that we just use standard rules for how we expand products involving parenthesized expressions. So nothing new here is going. Nothing new is going to happen here.
I'm sorry.
Yep.
This total degree of the polynomial won't be 5, just 1.
The total degree of the polynomial will be 9, because for every monomial, the total degree of the monomial is the sum of all the individual powers that we have. So if you write down this monomial, what's the logic here? So if you write down these powers explicitly, what's a power? A power is basically a product where all the terms are equal, right? So you can write this down as x times x times x times y times y times y times z. So the total number of variables then in this product will be 9, right? So then the total degree of this monomial is 9, the sum of powers of these variables in it.
And in what case we take the higher degree of sum?
we just have the definition of the degree of monomial, the total degree of monomial, and we have a definition of a degree of monomial over any specific variable, right? And then we use this different definition for monomials to define different degrees for polynomial. But still the concept is the same. The degree of polynomial is still maximum of degrees of monomials. Just we take the total degrees, but or the degrees over some variable. So that's it. Polynomials actually form a very important object in algebra, because without polynomials you cannot do much really. Even in computation, we cannot really go on without dealing with polynomials. We'll define in our course, we'll define several algebraic structures which behave much like standard number systems. So we have reals, okay? And what can we do with reals? We can add them, subtract them, multiply, divide, okay? So that's what we can do with them. Well, actually lots of things. We can solve equations, etc. And it turns out that we can construct sets of objects that are finite, but that behave much like all real numbers. Well, the cardinality of this set is infinite. We have lots and lots and lots of reals, and they cannot fit into the memory of our computers. So all our computers have finite precision, right? So we cannot compute arbitrary expressions involving real numbers with arbitrary precision. It's not possible. It is very convenient in computer science thus to invent some finite collections that still have much the same properties as real numbers that we can use in place of real numbers, so to say, to keep the infinite precision, but using finite memory, finite processing time, so to stay within our computational realm. And to create such rich set of numbers that are still very small, we'll need to use polynomials. So it turns like that. Okay, so the question on Zoom from Masood: is it possible to have rational powers in polynomials? Well, in polynomials, no. It's not. We do not consider rational powers because any polynomial is still essentially just a collection of monomials, and every monomial is just a product of variables. So again, every monomial can be written down just like x times x times x, etc. And with rational powers, we cannot immediately write down a monomial like this elementary kind of product involving only individual variables and a coefficient here. Well, in polynomials, we take only non-negative integer powers of all the variables. All right, so next we have our first definition. Yeah. How much time do we have?
10 minutes left.
10 minutes, okay, perfect. So let's start with our first important definition. And then, don't worry, this definition will be pretty abstract. But abstract can be made concrete when you consider lots of examples, right? So when we, at school, when we first learn to multiply numbers, that also sounds a bit abstract. Why should you consider a summation where all the terms are equal, right? And why it is important to learn multiplication table by heart? Well, that's because it simplifies things a lot later on during the study. So it goes the same way with much of the abstract things that we do in algebra. So we introduce some pretty abstract thing, then we provide examples to make it understandable, and then we actually use that thing for like computational purposes. So we'll start with the definition of a group. Group. Definition of a group. A group is the simplest, well, it's not really the simplest. We have even simpler definitions like monoid, but I will not define it probably in our course, just to not to overload. And it's not very important for our purposes. So that's the definition of so-called algebraic structure. Have you already learned a bit of Python? No. Not yet. Okay. So then I will not provide an example with duck typing because it is well specific to languages like Python, say. But okay, the algebraic structure. So in college mathematics, we have lots of sets of objects, collection of objects, but they are not just on their own. We can do something special with them. Okay, so we can use these objects, combine them in a way, and get some new objects. For instance, well, numbers are the first abstract things that we learn really while we're very small kids, and we at that time we already learned that we can do something with numbers. We can add two numbers to get a third number, right? So we can operate with these objects. We can compute something, and the more operations we require, the higher structure of the objects we actually get. So for natural numbers and for integers, well, let's start with natural numbers. For natural numbers, we can like add two numbers always, right? And get a different natural number. But if we like to subtract, we do not necessarily get a natural number anymore, right? So when we subtract a larger number from a smaller one, we fall out of this simpler set. So we have to learn something new. And we now get negative numbers, right? So and when we first start learning like about negative numbers, it's a mind-blowing concept. Like what's this? And we get the set of integers. Now here we can both add and subtract, but then we'd like to also multiply, and we can multiply here as well. The rules here are pretty mind-blowing again. So when we first learn them, so why by multiplying two negative numbers we get a positive number, and by multiplying a negative times a positive we get a negative? Oh, that's really mind-blowing. But then we cannot divide, right? So, but we'd like to divide one number over the other one. We would like to divide like 5 over 3 and still consider it as a decent like object. And within integers, we cannot do that always. Sometimes we can, but not always. And then we have to consider like rational numbers, right? And then we'd like to probably take some other operations like taking, square roots. And we cannot always take a square root without falling out of this set into a larger one. And then we would like to take square roots of negative numbers. And we cannot always do that unless we fall into a larger set. And here we can do pretty much everything. But the pathway before we reach this one is pretty long, right? So how many years actually pass before our brain evolves to such a state when we can understand how we work with complex numbers. So, and these all sets that we have here, they form a very standard piece of algebra, which is called algebraic structure. An algebraic structure is a set with some operations on this set that you can do. So you basically state, okay, I work with these guys, with collection of these objects, and I can do the following things to them. I can add them, subtract them, multiply them, or I can, whatever thing you imagine. Okay, so however you want to call that. Now you have to properly define what operations you want to have on your set, and what properties you would like your operations to have, and then you have an algebraic structure. So all these sets, like natural numbers with addition, integers with addition and subtraction, rationals with addition, subtraction, and say division, each of them forms an algebraic structure. And groups are the simplest form of algebraic structure, well, for us. So this is really an example, our first example of an algebraic structure. Algebraic structure. A group is a collection of arbitrary objects. So it's an arbitrary set. And well, you know that everything is usually notated by the first letter of the word in the definition. So groups are usually called G's or gammas. Greek, the same for Greek G, right? And in Russian, you know that Cyrillic alphabet was actually stolen from Greek alphabet. And so we have this gamma letter as well. So arbitrary set G with an operation on this set, with an operation on this set. What's an operation mathematically? What's that? This is essentially a mapping that allows you to take an object or several objects from a set and compute some new object from the same set. Okay? So in our terms, an operation is really a mapping from, well, maybe Cartesian square of a set onto itself, etc. So this is an operation. Okay? So this is an operation. It takes one object and computes some new object from the same set, basically, from the set of, like, you can consider this to be an operation on integers, on positive integers. Then taking a positive integer gets you a positive integer as well. But you can consider the same thing as an operation of, say, reals, because, like, you can take a real number, a square of a real, and get a real number. Okay? Now, if you consider this guy, then this is a genuine operation on, say, Zahlen, on integers, because you can always subtract 3 from an integer and get an integer, but not necessarily positive one. But you cannot consider this to be a genuine operation on the set of all naturals, because it is undefined when we take like 0 or 1 or 2 and try to perform this operation. Okay? So an operation is a thing which is always defined, okay, properly defined. Whatever you feed to this guy, you always know how to compute the result. This is a unary operation. A unary means, you know, one, right? So it takes one object and produces a result. A binary operation is an operation which takes two objects and produces a single result. So, for instance, addition or subtraction of two given numbers or multiplication are binary operations, right? So they take two elements and produce a single one. And the group is actually an arbitrary set with a binary operation on this set. And, well, we'll have a list of properties here which are very natural and which actually they happen for lots of different examples, not necessarily the number systems, but lines and other kind of stuff, so we can provide multiple examples of groups later on. Today we'll just stop at this point to continue later on, and we'll like complete this definition of a group on the 4th class today. Okay, so for now that's it.